This is Game AI Uncovered. My name is Paul Roberts, and in this video we're going to be looking at basic steering behaviours. First off, we have the seek behaviour, and we're going to see how we can get this zombie to seek towards its prey. It is currently moving, so it will have a current velocity, and the position of the unsuspecting human will be its seek position. So we need to get the vector from the zombie's position to the seek position. This is simple. It's just a matter of subtracting the seek position from the zombie position, and we're going to call this vector v. But really, all we need is a direction, and that is the vector v normalized, or in other words, pointing in the same direction but with a length of 1, the unit vector. And with this information, we can calculate the desired velocity the zombie wants to move at. This equals our unit vector multiplied by the zombie's maximum move speed. Okay, so this is all the information we currently have. But what we really need is a seek force. This is a vector that can be applied to the zombie and move it in the desired direction. This is simply our desired velocity minus our current velocity. Notice how it doesn't quite reach the target? That's okay. Each frame this will be recalculated and the calculated seek force will get us there, but it will overshoot because the seek behaviour doesn't cater for slowing down. Next up we have the flee behaviour. This time we're going to look at our human looking to get as far away from the zombie as possible. The only difference between a seek behaviour and a flee behaviour is how we calculate that v vector. For flee, we need to get the vector from the zombie to the human. V here is exactly the same vector as we saw in the seek example, but it's facing in the opposite direction. We need the unit vector of v to calculate our desired velocity, which we then multiply by the human's maximum movement speed, just as we did with the seek behaviour. This is all the information we need to calculate a flee force, and our flee force is our desired velocity minus our current velocity. This results in our human moving away from the zombie. So, on to the arrive behaviour. If you remember, I said the seek behaviour doesn't cater for slowing down. Well, that is where the arrive behaviour comes in. If you want your agent to stop at a point, this is the behaviour to use. This time, our zombie is a long way from where it wants to be, but just as before, we calculate the vector v. That's the vector from its current position to the arrive position. And this is done by subtracting the arrive position from the zombie's current position. And this is where arrive differs from seek. Instead of getting the unit vector of v, we multiply the vector v by some deceleration value. That's the value between 0 and 1. In this example, I've gone with 0.5. But as you can see, this is still faster than the zombie's maximum speed, so we need to truncate it, leaving us with our desired velocity. Now we can calculate the arrive force. This equals the desired velocity minus its current velocity, which will result in a movement something like this. And if we repeat the process, you will see the zombie makes its way towards the target position. Notice here how the maximum speed is greater than vector v multiplied by the deceleration value. When this happens, we don't need to truncate it, and this becomes the desired velocity. Looking at the previous positions of the zombie, you can see how it's slowed down upon its approach. Right, time for something a little different, the wander behaviour. We're going to look at two different ways of achieving this behaviour. With the first approach, place the zombie at the centre of a unit circle pointing towards its current facing direction. Then select a random point with which to face. As you can see, the unit circle goes from 1 to -1. So you can do this by randomly selecting a value in that range, but you'll need to choose whether that's on the left or the right of the circle. However you do it, you then project the circle ahead of the zombie and shrink the circle down. The important point here is that you don't want your agent to be inside the circle at all, otherwise you will get some odd behaviours. Then that random point on the circle that you projected ahead becomes the seek position, so you just call the seek behaviour and pass through this position. If we repeat this process, you can see how the zombie meanders across the environment. The second approach is even easier. Simply rotate the current facing direction some number of degrees either left or right, and then seek towards that position. In this example, it's rotated around 5 degrees. As you can see, the zombie still meanders across the environment. Next up, we have the intercept behaviour. Another issue with the seek behaviour is when the target is moving, if it moves as fast as your agent does, your agent might never reach the target. So we have intercept. This is a behaviour that attempts to predict where the target will be in some given time, but determining how far to look ahead is a tricky concept. But if we use the vector from our zombie to the opponent, the maximum speed the zombie can move at, and the velocity of the opponent, we can calculate a prediction time that is proportionate to the distance between them, the vector v, and inversely proportionate to the zombie and the opponent's speeds. To calculate a prediction time, we take the length of v and divide it by the maximum speed added to the opponent's current speed, or as you can see in the formula, the length of the opponent's velocity. It's the same thing. And with this prediction time, we can now calculate the intercept position. We start with the opponent's position and add on to it the opponent's velocity, which is multiplied by the prediction time, which results in a position ahead of the opponent, and our simple seek behaviour comes in useful once again. The evade behaviour is to the intercept behaviour what the flee behaviour is to the seek behaviour, or in other words, it's the opposite of intercept. Our human here follows the exact same steps described before to get a predicted position where the zombie will be in some time, but instead of seeking towards that position, it calls the flee behaviour and passes through that position to evade from. For the final behaviour we're going to look at in this video, we have two approaches to obstacle avoidance. But for both, we need our agent to have what we call whiskers or feelers. These are points projected ahead of our agent that look for collisions. And the faster the agent moves, the longer the whiskers extend. The first approach deals with colliding with other agents in the world. Our zombie here picks up speed and its whiskers extend into the distance. At the point a collision is found, on any of the whiskers, the point of the collision is used as the point to flee from. The zombie will slow down and its whiskers retract until it's safely past the obstacle. But this only works on smaller objects. Approach 2 deals with bigger objects. The first approach works because we can simply flee from the position of the object, but larger objects are trickier given the centre of the object can be far away from the point of collision. At the point a whisker has been found to collide with a big object, we need to respond to the whisker deepest into the collision. Take the whisker's current position and the point of collision and determine how far the whisker penetrated the object. And using the centre of the object and the agent's position, calculate the vector v, just as we've done throughout this video, but this time we're going to call the unit vector a repel direction. This is the direction we want to force the zombie to ensure that we don't collide with the object. But the force we want to propel the zombie, well, that's the length of the whisker penetration vector. And we get that by multiplying the two together. Returning this force will ensure our zombie moves around the obstacle. And on subsequent frames, whiskers may still be colliding, but these will be penetrating the object less and the agent will be moving slower. So before you know it, the zombie has avoided the collision. This has been Game AI Uncovered. Thanks for watching. Before I sign off, if you have an interest in Game AI, check out these books. Artificial Intelligence in Games covers all of this in great detail and supplies code samples for you to use. And the Game AI Uncovered series is filled with insight from professionals about how they did the AI for the games that you love.